Welcome to this tutorial on IAM policies and defining permissions. In this video, we'll learn how to write JSON policies for fine-grained access control in AWS IAM policies are the foundation of security in Amazon Web Services, allowing you to precisely control who can access what resources and what actions they can perform. By the end of this tutorial, you'll understand the structure of IAM policies and how to create your own custom policies to secure your AWS environment. IAM policies are JSON documents that define permissions for AWS resources and actions. These policies are written in JSON format, which is a standard data interchange format that's easy to read and write. Policies control access to AWS services by specifying what actions are allowed or denied on specific resources. They can be attached to users, groups, or roles, making them flexible and reusable. Most importantly, IAM policies enable the principle of least privilege access, meaning you grant only the permissions necessary for users to perform their tasks, nothing more. Every IAM policy follows a standard JSON structure with core elements. The version element specifies the policy language version, and you should always use 2012-10-17, which is the current version. The statement element is an array that contains one or more permission statements. Each statement must include an effect element that specifies whether to allow or deny access. The action element defines which API operations are permitted or restricted. Finally, the resource element specifies the target AWS resources using Amazon resource names, or a RNS. Understanding this structure is crucial for writing effective IAM policies. The effect element is a required component of every IAM policy statement and can have only two possible values. When you set effect to allow, you're granting explicit permission to perform the specified actions on the specified resources. Conversely, when you set effect to deny, you're explicitly blocking access to those actions, regardless of any other permissions. It's important to note that deny always overrides allow. This means if a user has an allow statement for an action, but also has a deny statement for the same action, the deny takes precedence and access is blocked. The action element specifies which AWS API operations are allowed or denied by the policy. You can specify a single action, such as s3:getObject for retrieving objects from S3. For multiple actions, you use a JSON array with comma-separated values, like s3:getObject and s3:putObject. Actions support wildcard patterns, so s3:* means all S3 actions. You can even use a single asterisk to represent all actions across all AWS services, though this is generally not recommended for security reasons. Each action corresponds to a specific API call in AWS. The resource element specifies which AWS resources the policy applies to using Amazon resource names, or a RNS. For example, to target a specific S3 bucket, you use an ARN like a RN:, AWS: S3: my dash bucket /*. The asterisk at the end means all objects within that bucket. You can specify multiple resources using a JSON array, allowing you to grant permissions to several buckets or resources at once. For DynamoDB tables, the RN includes the region and table name. While you can use an asterisk to represent all resources, it's best practice to be as specific as possible to maintain proper security controls. The condition element is an optional but powerful component that enables fine-grained access control. Conditions allow you to specify circumstances under which a policy statement is in effect. Common condition operators include string equals for exact text matching, date greater than for time-based restrictions, IP address for network-based controls, and bool for true or false checks. In this example, we're using the IP address operator to restrict access to requests coming from a specific IP address range, and a bool operator to require multi-factor authentication. Conditions are essential when you need to implement advanced security controls like restricting access based on time of day, source IP address, or whether MFA is enabled. The principal element is used in resource-based policies to specify who can access the resource. You can specify a specific IAM user by providing their full ORN, which includes the account number and username. To grant access to an entire AWS account, you simply provide the 12-digit account number. For AWS services, you use the service key with the service's domain name, like ec2.amazon.aws.com. You can even use an asterisk to make a resource publicly accessible, though this should be done with extreme caution as it allows anyone on the internet to access the resource. The principal element is not used in identity-based policies, only in resource-based policies like S3 bucket policies. Let's look at a complete IAM policy example that grants read-only access to a specific S3 bucket. The policy starts with the version element set to 2012-10-17. The statement array contains one statement object. The effect is set to allow, granting permission. The action is S3:getObject, which allows downloading objects from the bucket. The resource element specifies the exact bucket using its ARN, with an asterisk indicating all objects within that bucket. This simple but effective policy allows a user to read objects from the my-bucket S3 bucket, but prevents them from uploading, deleting, or modifying any objects. IAM policies can contain multiple statements to combine different permissions in a single policy document. In this example, we have two separate statements within the same policy. The first statement grants both getObject and putObject permissions on an S3 bucket, allowing the user to both read and write objects. The second statement grants getItem permission on a DynamoDB table named users, allowing read access to that specific table. Each statement is independent and evaluated separately. This approach keeps related permissions organized within a single policy document, making it easier to manage and audit. You can have as many statements as needed in a single policy, though it's best to keep them logically organized. This example demonstrates fine-grained access control using conditions to add multiple layers of security. The policy allows all EC2 actions, indicated by EC2:**. However, access is restricted by two conditions. First, the IP address condition ensures that requests must originate from a specific IP address range, in this case, 203.0.113.0/24. Second, the bool condition requires that multi-factor authentication must be present and set to true. This means even if a user has valid credentials and is connecting from the allowed IP range, they still need to authenticate with MFA to perform EC2 actions. This layered approach significantly enhances security by combining multiple verification factors. Let's review the best practices for writing IAM policies. Always apply the principle of least privilege by granting only the minimum permissions necessary for users to complete their tasks. Use specific resources and actions rather than broad wildcards whenever possible. Avoid using wildcards for resources, especially the asterisk that grants access to all resources, as this creates security risks. Regularly review and audit your policies to ensure they still align with your security requirements and remove unnecessary permissions. Use conditions to implement fine-grained control based on factors like IP addresses, time of day, or MFA status. Finally, always test your policies using the IAM Policy Simulator before deploying them to production. This tool helps you verify that policies work as intended and don't inadvertently grant or deny unexpected access.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.